To recap, our Riemann sum has a limit that we call the definite integral as the norm of the partitions for which we've divided up our interval from a to b tends towards 0 of that summation from I equals 1 to n of f of c of I delta x of I, and we call that the definite integral. And we've actually seen this process when we took our definite integral before. We said that for every c sub I inside of our interval, right here, we might call this one c sub I right here, we say within every interval f of c sub I, we say that whatever the delta x is for each of those c sub i's right here, and we take that sum, as we let those intervals get smaller and smaller, we can fit more of them underneath that curve, and so our estimate gets better and better. And we're taking this limit right here to be equivalent of saying when we had a fixed number of n rectangles underneath a curve, that we let that n tend to infinity. So as n tends to infinity with our fixed rectangles, it's the equivalent of stating that the norm of our partitions, because if all of the partitions are the same size, the norm of our partitions will tend to 0. So we think about this region, we call it the definite integral from a to b of the function f of x dx for which the region is drawn under. Right? Now, if f is continuous and non-negative on the interval, right, we say that this is actually the area, but we want to make sure that we understand that we're not necessarily always talking about area, but we definitely do get a fixed number from our definite interval. That is definite integral, pardon me. So how would we do that? Well, we're going to get into the connection between this because we've seen this symbol before when we were taking antiderivatives. And there definitely is a connection, but for right now, let's just take this to be our definition. And we're saying, all right, if we have a curve whose area is above the x-intercept, we can certainly go through and we can estimate some areas right here. Like, let's talk about this one. Let's say we've got the curve y equals 2x plus 1. And it says, let's evaluate the integral. And we can use some common geometric functions to really express this one, right? So we want to go from 1 to 3. So we imagine that we draw an area, or region, between 1 and 3. And so we're interested in finding the area under the curve here. All right, what is the value of this region here? Well, for our purposes, we can actually see that this shape is a trapezoid. In a trapezoid, we know that there's a formula that goes kind of like this. It says for a trapezoid with base 1 and base 2 and height h, the area would always be given by 1/2 h times base 1 plus base 2. So let's look at our shape over here. What's base 1? What's base 2? What's our height? Well, the bases are the unequal portions of our definite integral right here. So we're going to take this region right here. This is going to be our base 1. And it looks like this is going to be our base 2 over here on the side at 3. Our height is going to be the part where we have between our two parallel sides right here. So that means that we have to make our height right here. Okay, so in this formula, what is that going to tell us? Well, we know that our height is equal to 2, right? That's because we're taking the endpoints 3 and subtracting 1, and we're getting that. For our bases, base 1 is going to be the value of the function at x equals 1. So we're going to take base 1 to be 2 times 1 plus 1. So that will be equal to 3. And you can certainly see that's the y value right over here. And of course, base 2 then is going to be 2 times 3 plus 1. And we know that that's going to be 7. Again, we can verify that on our graph right here. And so putting together the information, it looks like our area, which is our region that's bounded on the interval from 1 to 3 over the x-axis and under the curve y equals 2x plus 1, would be equal to 1/2 of 2 times 3 plus 7, base 1 plus base 2, and that, of course, is going to come out to be 10. And so our area under the curve right here should be 10. Not too bad. More to come in the next video.